What are the two doses that you have?
There's 6 and 2.
Okay, what does the 6 go to?
The dose in gray.
What kind of what kind of radiation? I mean.
X-ray. Yeah, X-ray.
Specifically, what kind of X-rays?
X-rays should cause erythema. Erythema? Oh yeah.
What does it say right before the X-rays?
KBP. 6th grade of 250 kbp X-ray to cause erythema.
That's right. So the 250 kbp X-ray, right? That is our baseline radiation.
Oh, okay.
For RBE, we always compare the 250 kbp X-rays, right? And so the dose of our baseline, the dose of that 250 kbp X-rays is 6 grays. So that's the number that goes on the top. In that case, the radiation that we're looking at is this radiation C. What is the dose of radiation C? 2. Right? So we've got 6 on top, we've got 2 on bottom, 6 over 2. Shaheen, what does that give us? 3. So the RBE is 3. That means radiation C is 3 times more dangerous, right? 3 times more effective at causing this erythema. Yes?
So what sort of unit is that? Do we just do RBE, 3 RBE, or 3 gray?
Great. So is there a unit for RBE?
Okay.
Is there a unit?
I don't think so.
There is no unit for RBE.
Thanks.
It is just a plain 3. That's right. The units cancel out, so this is a unitless value.
Oh, okay, yeah. Okay.
Right, the grays and the grays cancel out. Okay, speaking of units, what about LET? LET, linear energy transfer. Okay, team.
That's
What is the unit for LET?
kilo electron volts over microns.
Okay, so that's right, Jay. Kilo electron volts over microns, right? Because it's energy over distance. Okay, and then OER. Veronica, what do you think the units of OER are going to be? Once again, no units. It is unitless. Okay, so just remember, LET is the only one out of these 3 that actually has units. Okay, RBE, OER do not have units. So, John, do you have a question?
Yeah, for those questions, do we have to write that it doesn't have units, or can we just leave it blank?
Make sure that you tell me that it has no units.
Okay.
If you leave it blank, I'm going to assume that you
Didn't know.
didn't know and you didn't answer. So just make sure that you write down, right?
So
It
this
does
one
not
would
have
just be
units.
3.
Just do a star and write units cancel out.
So, question 3, the RBE is 3.
Well, if you
Yes.
don't see nothing, then you ought to know that it's no units. That's just common sense.
Oh.
So,
But since
because the question specifically asks, right, what units does it use, right? I want it written somewhere in here that it does not have units.
But
This
if
is
I
how you
wrote,
calculate RBE.
I
it
know,
does not
but
have
if I wrote
units.
3 and I circle it as my answer and I don't put nothing, then you should.
I can't take that
Oh,
because
Mr.
otherwise you'll have plenty of people that are going to answer question 1 for the LET, not put units, and then I'm going to have to count all of those wrong. So I can't make assumptions like that.
So LET and RBE, no units.
OER.
I'm gonna write it real big, no
RBE
units.
and OER have no units.
Oh,
LET
shoot.
does.
Oh man, I just got confused. Okay, you said who got what now?
LET has units.
And who else got units?
That's it.
Okay, has units. Okay. Everybody else got units.
Everyone else got units. That's right.
So in the answer, if we put the units, we don't have to write out K.
What if it's
KEV
not
is
that?
the KEV over the micron is the unit, or like we don't have to have that whole sentence. We can just have the unit there.
OER and RBE,
So-
No units.
no units. Oh, well, I had it
Cool.
right.
Right.
Okay.
LET. Okay, these are the units for LET. On the other hand,
Upside down.
Does not
So-
have.
upside down thing?
So,
Sorry, hold on. Reagan, go ahead.
Oh, sorry. The KBP slash. What's that little under?
Oh,
Upside down.
this thing. This is so this is a Greek letter. It is the Greek M. It's called mu. We use this when we do micrometers because millimeters and micrometers both start with M. You can't use MM for both millimeters and micrometers, so they use this weird looking
So,
M
what number
instead for
What number
micrometers.
one be?
Or you could put
0.5
KBP
UM?
slash micron.
Number
Yep,
what?
this is fine as well.
Okay, never mind.
That's the unit?
Yes,
So is
50.
micrometer the same as micron?
Yes, they are the exact
Micrometer
same.
and micron.
They are the same.
Shamika, for number one, did you get 120?
All right. And then
Did I do
here,
it wrong?
okay, as far as RBE is concerned, right, notice I did make sure to put units for our doses, but RBE itself, right, has no unit afterwards. RBE
Gotcha.
is unitless. Same thing for OER, right? OER, you do have the doses, but the value itself for OER is unitless. No unit for RBE, no unit for OER. Yes.
Hey, Mr. Phung, on the first one, I want to make sure I'm kind of doing it right.
Okay.
It asks, hey, if radiation A deposits 120 keV over 1 micron, so I just put 120 over 1, and I put LET equals 120.
Okay, so that is the LET for radiation A, correct? Great.
Okay.
So
Okay,
you just
that's
keep
what I
doing
did.
that,
Okay.
do that for radiation B as well.
Okay.
And then look at the two, figure out which one has the higher LET.
Okay.
Yes, Cody.
For number 4 for the OER,
Yes.
it's talking about like oxygenated and deoxygenated.
Yes.
So is deoxygenated in relation to hypoxia?
Yes.
Okay, so then that would be the unit, or
Correct.
the, I guess the dosage for that part of the equation.
Yes.
Okay. And then the answer that I got from going off the PowerPoint,
Mm-hmm.
cause I got 1.04.
That sounds correct.
So, and on here it says that for like high LET radiation, it's gonna equal like approximately 1.
Yes.
So that would be like approximately like 1.
Sounds like good reasoning to me, yes.
Okay.
Very good.
Also a question about that, for the high LET one for the OER,
Yes.
it doesn't say anything about like dose. It just talks about just the, I guess like the multiplier. But
Right.
for low LET, you have to take into account the dose, right?
So what happens, because you see OER has the dose in the equation, right? So the thing is that with low LET radiation, because it's not directly hitting the DNA, it's not actually causing really big effects directly, the oxygen has a lot more opportunity to involve itself in the process of damage. So we find that in cells that don't have a lot of oxygen, you need more dose, right? In cells with lots of oxygen, you need less dose. And the difference in dose is significant. It is highly noticeable in cells with air versus without air. So our OER is going to be a relatively large number. It's not going to be close to 1. On the other hand, if you look at the doses for high LET radiation, in hypoxia and in air, the values are almost exactly the same. And the reason is because the damage from high LET radiation is so big that it does not matter if oxygen is there or not. The damage is done straight from that high LET radiation. We do not need to go to oxygen to create extra damage. So because the doses will cause similar damage, the doses are similar. If you have two similar numbers over each other, it will be very close to 1. So, keep working on those when you get home. For now, we are going to move into some new territory. I'm gonna swap the lights here. So, sorry, in back row, you're gonna be a bit brighter now. I mean, it's just a bit easier to see the screen. Okay. So, when we finished on Tuesday, we were talking about free radicals. Free radicals are these highly reactive atoms or molecules. They are highly reactive because they do not have a full outer electron shell, what we call the valence shell. That outermost shell, the valence shell, either has 7 out of 8 electrons, or it has 1 out of 8 electrons. Okay, so it's really close to having 8. It's just 1 electron off, either extra or missing.
So, are these the only two situations, 7 or 1?
Yes. Okay, sorry, a lot. Technically, you can have 2 as well if you're only dealing with the very first shell. Okay, so that's only going to apply to hydrogen. Yes.
Can you explain why the top row, the 1 doesn't have the L again?
Up top here.
Yeah. What had happened?
All right. So this here is an electron diagram.
Okay.
Each of these green things is an arrow. I'm not going to go into why, but you'll find out that electrons will always pair 1 up, 1 down.
Okay.
So in our first electron shell, right, the K shell, you've got 2 electrons, 1 up, 1 down. We go to our second electron shell. That can hold 8 electrons.
Okay.
So you've got 4 of them up, 4 of them down. Perfect. We go to our third electron shell. Now, this is chlorine. Chlorine has a total of 17 protons, right? Atomic number 17. Chlorine, in this case, does not have a charge. You notice it's not positive, it's not negative. So that means for each proton, we need a matching electron, right? 1 positive, 1 negative, they cancel each other out. So, right? 2, 4, 6, 8, 10. 10 electrons so far. We go to the outermost shell. 12, 14, 16, 17 electrons. So, we've got a full 17 electrons here to match our 17 protons. But, because we only have 17 electrons, we're missing the final one to fill up this shell. So, even though chlorine is electrically neutral, it doesn't have a positive, it doesn't have a negative, it's not an ion, chlorine is unhappy. It's like, I was so close to finishing off this shell. I was so close, 7 out of 8. I really, really, really want that 8th item, that 8th electron. And so because of this, chlorine becomes dangerous. Now it's stalking the streets. It's going around looking like, do you have my 8th electron? Do you have my 8th electron? And as soon as it finds someone that has an electron that looks kind of loose, it jumps them, beats them up, steals the electron from them, and then it's happy.
Why are you so violent?
It's not me, it's chlorine. It's the chlorine that's violent.
That's a little too basic of an answer
This
for me.
sister's getting
Okay, so, okay,
Nobody liked that one?
these types of atoms or these types of molecules we call free radicals. They really, really, really want to fix their outermost shell, and they will attack other atoms and molecules to do so. So, here we have water, H2O. 2 H's, 1 O. Okay. Now, this water floating inside our cytoplasm, an X-ray comes in, and it hits one of these chemical bonds. And the energy from the X-ray breaks the chemical bond. What happens? Okay.
1 strand.
So, X-ray comes in, right, ionization, right? Crashes into electron, electron comes flying out. So now this entire thing is missing an electron, right? So, this is missing an electron, right? This is still fine, right? But this hydrogen is missing an electron. So, because this is missing an electron, we end up with this break. Okay, so what happens? Well, on this side, we said our hydrogen missing an electron. So this one's a positive ion. Right? We said you take an electron away from something, it becomes an ion. So it's positive. But on this other side, this OH didn't lose an electron. So this OH is fine, it's not an ion. However, this OH really, really, really wants an electron because it's missing one. Okay? It feels like it's missing an electron. It really, really wants an electron.
But we
So-
just, sir? You just said radical doesn't have any ion.
Correct.
So then how come it's missing in
So it has the correct number of protons, the correct number of electrons, but it has an opening in the outermost shell. So this ion, it's fine. It's going to float away, but this here has become a free radical. Okay, this can actually happen. So now let's take a look at this electron that flew off. Right, so this electron got kicked out. The electron goes flying away, and the electron eventually runs into another water molecule. So the electron runs into another water molecule, it gets picked up, so this electron forces its way into here, again, right? It's kind of like a, what's the term for it? It's a home wrecker, right? This
But
electron
you know about
comes
that,
in,
Mr. Phung?
forces its way into this relationship, and it severs this relationship. Once again, we cause this break in our chemical
Or
bonds.
break up.
Right. This molecule has now broken up. The hydrogen and the hydroxide have parted ways because of this electron right here. And so, over here we have an ion. Okay, right? Extra electron, this becomes an ion. Over here, this hydrogen is normal, 1 proton, 1 electron. But now this hydrogen is unhappy. It wants to fill its outermost shell. So once again, this is a free radical. So we have now created 2 free radicals. We have the free radical over here from that original interaction, that hydroxide free radical. And over here, we have that hydrogen free radical created after the electron joined a different water molecule.
You're confusing me.
Okay.
Well, you're not confusing me. I'm just not
Right.
understanding.
Just take this as story time then. The process, not that important, okay? But this is just so that you know what is happening, why free radicals happen when X-rays hit this. Registry probably won't go this in depth, but it's fun. It's also in your book.
So it's just a free radical whenever
It
it's not
breaks?
paired up with an electron. That's it.
So, yes, so when it breaks apart, when a molecule breaks apart, right? And now it used to be connected to someone, right? But now it's alone in its relationship, right? It's no longer with someone, it's lonely, it really wishes it had another significant other, right? They become that kind of toxic person that like goes out and like just tries to hook up with anyone they can.
Oh my
Mr.
God.
Phung, there's
That's a
else.
whole story, man.
That's a free radical.
So that's what.
It needs a movie, man.
It's the one with the dots. This one here,
Okay.
and then this one here.
So,
Just think of radiolysis as like a very bad soap opera, okay? This is just a very bad soap opera.
so like she said, when the electron strikes something and
Yes.
it breaks them apart, that's when it becomes the free radical.
Right, so if you look at the movement of the electron,
A home record, like you
right,
said.
home record.
Oh,
So electron leaves, electron enters, right? Anytime the electron's moving around, we end up with an ion and a free radical. An ion and a free radical. Yes, Reagan.
So can it only be broken apart in this, like one specific way, like, or can it, like, they both,
He
like,
says a home record.
I don't know if that makes sense.
I see what you mean. So, in the end, regardless of what hits what and what breaks what, it will always end up with these 2 pairs of ions and these 2 pairs of free radicals. So
But
you'll
after
always
that-
have a hydrogen free radical and a hydrogen ion. You'll always have a hydroxide free radical and a hydroxide ion. Yes, Jay.
But after that, when there are other free radicals that start to form, do those break up after or start to constitute with other things?
We'll get to that. We'll get to that. So right now, we're just focused on water right now, radiolysis, right? Yes, Shahid.
the hydroxyl are the radical and the ion, do they mix, they can attach together and
They
form-
do not attach together, no. Instead, the things that attach together are just going to be the 2 ions. I've got an H here, H plus. I've got an OH minus. Plus and minus, right? These are opposites. We say that opposites do what?
Attract.
Opposites attract, right? So it's like, hey, nice to meet you, let's go on a date, and then these 2 get together. And if you put a hydrogen together with an OH, what does this become?
Water.
Water. So these 2 form back into water.
Smith.
On the other hand, these are not ions, so they do not pair together. Instead, they are the ones that go around and steal electrons from other molecules. So now these are the ones that wander over the DNA and steal electrons from the DNA. And when they steal electrons from the DNA,
It
once
destroys
again, it messes with those chemical bonds in the DNA. Okay, so it is these free radicals here that are primarily responsible for the damage. And in fact, it is this OH free radical that's actually the most dangerous free radical.
I thought you said they're not
You said
ions.
OH or HO?
OH.
Okay.
The
No, it's
regular-
OH.
Okay, I was just looking at how it was like kind of written.
Right? Well, it's not Christmas. We're past Christmas, so no Santa ho ho ho, right?
Yeah, I was just saying like, I was just saying they could be dangerous. You never know.
Okay. All right. Shaheen and then Shamika.
So radiolysis is the removal of hydrogen ion.
No, radiolysis is just the breakup of water, just breaking water. Right? How do we break water? That's when we have the whole electrons moving from one to another.
The term breaking of water is termed
Radiolysis. Correct.
How and what is not considered.
Okay, Shamika.
You said the ones that circle, they're not ions, they do not pair
Correct.
together, they go around and steal electrons from DNA.
Correct.
Okay.
So these free radicals, these are ones that go around and steal electrons. They can steal electrons from any molecule, but the molecule we care about is DNA. Right? They could steal molecules from proteins. They can steal electrons from like lipids and stuff, but that's not important. What's important is when they go and steal electrons from DNA.
So the point lesions are unique to DNA molecules or RNA?
So we specifically are going to be talking about point lesions in relation to DNA. Yes.
Okay.
So you say just drown me. Angelica, you said just drown me. I was ready.
Angelica was like, if she barely understands the weeds.
That's okay. Just think of it as story time, right? It was just a fun soap opera that you got to experience. But what is the key point to all of this, right? Once you get through all of this, what is the main important part? The important part is that when X-rays interact with water, they form free radicals. Right? When X-rays interact with water, they form free radicals. These free radicals are dangerous.
So we don't have to know how or anything like that. We just have to know that.
So, process, not that important.
Okay.
Right, so the whole, knowing which electron jumps where, I don't actually care that much about it.
Okay.
Right? It's just to kind of spice up the story a bit. But the main important part is that X-rays come in, you get free radicals out from water.
Okay.
And those free radicals are what causes our indirect action. Yes, John?
So radiolysis is the process and free radical is the outcome?
Yes. Radiolysis is the process, and free radicals are the outcome. Very good. Okay, now, it is possible for two hydroxyl free radicals to bond together. They give you hydrogen peroxide. Hydrogen peroxide, toxic substance to cells. Right, we use that for cleaning because it kills things. So yes, X-rays can produce hydrogen peroxide inside your cells. That's not good. It does not sound good. No.
It'll be bubbling when it touches your blood and stuff.
Exactly. Right? You don't want your
That's
cells
why
bubbling
Tim is so
from the inside.
toxic.
Okay. You also have this hydroperoxyl radical thing. Just ignore that. Not important. Let's skip past it.
Okay.
All right. Going to Jay's question, can these free radicals interact with other things? Yes. So they do interact with organic compounds, right? And you can also form free radicals out of organic compounds. Once again, not
Not
too
important.
concerned.
Click.
Oh.
Oh, never mind. I thought you said this one wasn't gonna be important too, and you was gonna go to the next slide. I'm sorry.
So I'm not too concerned with this, but I do want to point something out.
Okay.
If you look at this, right? So this R just represents a whole bunch of carbons. So this is like a carbohydrate, for example. So you can create a free radical out of a carbohydrate, right? And then you kind of free radicals come back together and kind of like repair themselves. But if you have oxygen, now suddenly it can react with the free radicals as well. And this goes back to the oxygen effect. Remember we said if there's oxygen in the cell, right, excess oxygen, the oxygen can also participate in these chemical reactions, and it can cause damage. It can cause extra damage to the cell. So that's kind of what you're seeing here, right? Oxygen is helping to increase damage to the cell thanks to these free radicals. So main takeaway from this slide, oxygen effect. All right, back to the important stuff. Indirect action summary. So let's summarize indirect action.
All right.
We've got a beautiful diagram over here. X-ray photon comes in, interacts with water. Water can either turn into ions or free radicals. These free radicals, through indirect action, can either produce toxic substances or they can go and directly interact with the DNA. The free radicals or the toxic substances interact with the DNA and they cause biologic damage. Right? So toxic substances, stuff like hydrogen peroxide. Right? So free radicals, hydrogen peroxide attacks DNA, causes biologic damage. Ions aren't as dangerous. Ions don't really cause that much damage. So this chart here is pretty much the key to take away from all of this. Yes, Cody.
So low LET is mostly caused by indirect action, but when we're talking about high LET, because
Yes.
I was reading it earlier, it says that primarily the cause is by like implantation, ingestion, like all that kind of stuff. Is that considered direct, or is direct different?
Okay, so those things that you mentioned, implantation, ingestion, inhalation,
Sorry,
what was the fourth one?
Injection.
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 Okay. So
Diarrhea?
those things are ways to introduce high LET radiation into your system, right? Because we were talking about how high LET, usually alpha particles, have a very tough time interacting with our body from the outside, because they can be blocked by so many things: sheet of paper, clothes, right? So the only real way for your body to experience high LET radiation is for you to have breathed in some radioactive substance that creates high LET particles. It's for you to ingest or to be injected with something that produces high LET radiation. So that's what those bullet points were referring to. And then, I'm sorry, I forgot the second part of your question.
Like, so is that process of all of that,
Mm-hmm.
does that lead to direct action?
Mhm. Yes, so once the high LET radiation is in your system and it's capable of interacting with your cells, high LET radiation primarily damages your cells through direct action. So if you see indirect action, immediately associate that with low LET, X-rays. If you see direct action, associate that with high LET, alpha particles.
Okay.
But regardless of this is indirect or direct, the end result, damage to critical molecules of the cell. And what is the most critical molecule in the cell?
What the DNA cell.
DNA. That's right, DNA. So, let's take a look at how we can damage DNA.
So
Yes.
now
Shahid.
that there has to be is DNA more critical or is water more critical?
How many DNA molecules does your cell have?
46.
Okay, they're all unique molecules, correct?
They're all unique.
All unique. You don't have extra copies of them hiding around somewhere.
So they're more special than the water molecules,
That's right,
which are
so-
very common and ordinary.
Right, so if I destroy 23 water molecules, is the cell going to survive?
With if you destroy the water molecules.
If I destroy 23 water molecules, will the cell survive?
I would think dehydrate, it will dehydrate.
How many water molecules do you think are in the cell?
Oh, millions maybe.
Mm-hmm.
Okay, sir.
So if I destroy 23 water molecules,
Nothing will happen.
nothing happens. If I destroy 23 DNA molecules,
Many things.
your cell dies, exactly. DNA is the most important molecule in your cell. Okay, so how can DNA be damaged? The first way is through something called a single strand break. So this is our double strand DNA, and if we take a look here, we have this break in our chemical bonds. So there's a break in the chain of our DNA, but only on one of these chains. You don't see a break over here, right? It's only on one side. Okay, so this is our point lesion. I think Jay was asking about that earlier as well. Okay, so this is our point lesion in reference to DNA. It breaks one of these sugar phosphate side chains. What causes single strand breaks? Usually low LET radiation. Right? You've got an X-ray, it's bouncing around, it goes bloop, causes damage, and then it just leaves. It doesn't stick around to do any extra damage, it just does a bit of damage and then leaves. So single strand breaks are considered to be low levels of damage. These can be repaired with enzymes. Okay? Your body's like, hey, something's broken here, enzyme comes in, fills in the crack, and then your DNA is good as new. So single strand breaks are not as dangerous. They're not as critical to the body. On the other hand, if you have a double strand break, so now both of those chains are broken, that is a serious issue. So double strand breaks, right, affects both chains. So it's not that one chain gets broken twice, it's that each chain now has a break in it. Now, if these breaks are far apart, if one's broken all the way here and one's broken all the way here, okay, not a big deal. That's manageable. But if both of them are broken at around the same location, what do you think is going to happen?
It will detach from
So, if you just look here, right? If I just cracked it here as well, break here, this entire thing can now separate, right? It can completely detach. So, if it completely detaches, now you have a major problem with the DNA. Now your DNA is in pieces, right? So if these double strand breaks are close together, you can it's pretty much the same as just snapping the entire chromosome. So why would these two strands really close to each other end up breaking? Because of high LET radiation. Alpha particle comes in, right? So giant alpha particle comes in, and it goes boom, boom as it travels. Right? Both of them were in the way of the alpha particle. Alpha particle broke both bonds. You now have a double strand break, and the cell is in trouble. Yes?
So if they're far apart, they completely break right there, or is it when they're close together they break?
So when they're close together, they'll
Okay, all right.
So as an example, again, if this one breaks, and then like
And that
this one all the way up here breaks,
That's
you have
okay.
all this stuff kind of like holding it together still,
Uh-huh.
so it's not gonna fall apart as easily.
Okay.
But if they're right next to each other, then this can easily detach.
Okay.
Yes, Jay?
So then, would it be okay to say that high LET can cause single and double strand?
Yeah. So both of them can cause single and double strand, but low LET is more likely to cause single strand, high LET is more likely to cause double strand. They can cause either or, but low is more likely to be single,
Okay.
high is more likely to be double. So if we do snap the chromosome in half, right? If we do have a double strand break, very hard to undo that damage, right? Because just right. So it's like this is my DNA, and then it gets broken completely, double strand break, and now the cell's trying to put these two chromosome pieces back together. It doesn't know if it puts it together like this, or like this, or like this, or like this. Very hard to figure out how to repair this now that the DNA is in pieces.
And it can also go to other pieces of chromosomes?
Yeah, it could even end up with other pieces of chromosomes, right? So you have a piece of chromosome 13 stuck onto chromosome 16. So lots of problems can happen when you have chromosome breakage. All right, so here's our diagram. I should have used this one. Right, so there's our double strand break. Both of these are broken, so this can easily detach. Yes, Cody.
So like, so you could say that like double strand breaks are more dangerous because they could completely detach, which would kind of result in like the destruction of the chromosome itself, versus destruction like the wrong word.
So I'm not. Yeah, destruction seems a bit too extreme. It's not like the whole chromosome is dead, but now you just have these two pieces. So it's kind of like you had a book and now you rip the book in half. So you can use like the first half of the book, you can use the second half of the book, but ideally you'd want the whole book together.
So I have a question.
Shahid.
So this is all, the first image is also a double strand break.
Yes, so these are both double strand breaks.
But this is not so dangerous.
Right, so far apart, not so dangerous. Close to each other, very dangerous.
The distance is the same, it's only the location, so.
Distance like this.
Yeah, but you know.
So this is,
That's the
so if this is, if I count them right, 1, 2, 3, 4, 5, 6, it's 6 spaces away. This is at exactly the same location. All right, so I'm talking about height-wise, okay, height-wise. So these single and double strand breaks can lead to mutations. Right, so changes to the DNA are called mutations. So mutations can come because we have added base pairs, changed base pairs, removed base pairs, but something happened to the DNA. If there is a mutation to the DNA, what happens? Well, maybe the cell catches the mutation and they fix it, they repair the mutation. Maybe the mutation is in a critical part of the DNA and the cell just dies. Or maybe the mutation doesn't do something which damages the cell, so the cell lives and is able to replicate and pass that mutation on to the next generation of cells. Right? If it's in a somatic cell, the somatic cells will just keep replicating and you'll see this mutation inside the somatic cells, the body cells. It's not like these are going to get passed on to the children, right, the kids of the person. It's just going to be those body cells. And finally, examples of mutations, we have frame shift, point, and chromosomal alterations. Of these mutations, we are going to focus on chromosomal alterations. We're going to briefly talk about these, but the important one is chromosomal aberrations. All right, so let's take a 10-minute break. Please be back at 1:10. And mutations, right? These aren't that impressive. It's not that impressive. Not that impressive. So here, this diagram here just shows you all different sorts of DNA mutations, right? You have your chromosomes. You see things getting deleted. You see things getting added. You see things getting flipped around and moved around and chopped up. So these are all things that can happen when you have those chromosomal breaks. Right? Your chromosomes can move all around and cause issues, mutations. Right? We've also got point mutations. These are just examples. Right? You have changes to the DNA. And remember, DNA gives you the instructions for mRNA, and mRNA gives you the instructions for proteins. So by changing your DNA, you change the kind of proteins that your cell creates. And so you can cause a lot of issues that way as well. Now, this one is pretty important. Covalent crosslinks. Crosslinks. Sounds familiar, doesn't it?
Yes, from the first or second semester.
That's right, we talked about cross-linking before. So, what is cross-linking? We said that when two parts of a molecule attach to each other when they're not supposed to. In this case, our molecule is DNA. So we end up with a chemical bond between two parts of our DNA that should not be there. It can be between two parts of the same strand. It can be between two parts of different strands. but this bond should not be here. And when there are these bonds, then they can cause issues in reading the DNA or the function of the DNA. Any weird chemical bonds will cause issues for the cell. In this case, covalent crosslinks, the cross-linking is between the same strand or different strands of DNA.
Either or are considered covalent crosslinks?
Correct, both of them are covalent crosslinks. So within the same strand, that is intra-strand, intra meaning within. Between two strands is inter-strand, inter meaning between. All right, now the really fun part, chromosomal damage. So if you look over here, you can actually see these chromosomes. These are chromosomes that you can actually see under a microscope. So this takes place during mitosis, right? So during metaphase, right, when you can see these chromosomes trying to line up in the center, you can actually physically see them, right, with your eye, using a microscope. And you can physically see damage to the chromosomes as well. You see here that the leg of the chromosome has been chopped up, right? Here is one of our double strand breaks. Both strands of the DNA broke, and so the entire thing came off.
Which one?
So it looks like one strand broke, sir. Because
So,
the other
just
strand
remember,
is okay.
just remember, this leg
Is
is
one
made
strand.
of a double-stranded piece of DNA.
Or one strand is, so, these are two strands.
These are
that-
sister chromatids.
There are two
This,
strands.
this one right here, so this line, including the break here, that is a single chromosome.
Yes, sir.
A single chromosome is made of a molecule of DNA. The molecule of DNA has two strands. So this thing here has two strands inside.
On
This
the-
thing here
oh, I see.
has two strands inside.
Right, sir.
So because there's a break here, both of the strands in this one had to have broken.
Right, sir.
Now, you can see that we've got all of these different fragments of DNA here. Okay, all these fragments of chromosomes. And so these fragments, they could try and reattach to the correct chromosome, or if they're unlucky, they might end up reattaching to the wrong chromosome. So once again, chromosomal breaks like this, very dangerous. So, the next question becomes, when did these chromosomal breaks happen? If you look at our example image here, you see most of these breaks are only one of the two sister chromatids, right? You've got two sister chromatids, but only one of them is broken. Two sister chromatids, only one is broken. Two sister chromatids, only one is broken. So only one of the two sister chromatids shows damage. If you think about the cell cycle, G1, S, G2, mitosis, when did this damage happen?
In synthesis.
So Mansi, I heard you say G2. Shaheen, I heard you say S for synthesis. What else, what did the rest of you think? When do you think this damage happened? So let's make it
S.
simple. G1, S, or G2?
This.
S? Okay.
Where did, what?
So, you see how we have our sister chromatid here, but only one of them is broken. The other one is fine. So when do you think this damage happened? Did this break happen during G1, S, or G2? G2, G2, G1, G2. Okay, so someone who thinks
It just happened.
G1, what is your reasoning for saying that this happened during G1? Or did G1 just sound like a nice answer?
No, well, G1 is where like the original,
Mhm.
I guess sequence is,
Mhm.
then it goes to S, then G2 double check the,
Mhm.
I don't know, just thought if it was initially broken, then
Okay, so you thought that, okay, it was broken initially, so that had to have happened in the G1 phase. Okay, so Someone who thinks S. Why do you think this happened during the S phase?
So
Becky?
because duplication is taking place, and while the duplication is taking place, something can detach and something can happen, sir.
So you think it broke off during the process of replication?
Yes, sir.
All right. And then someone who thinks G2. Why G2?
Because in comatid arbitration, you still have one sister that's normal, the other is broken.
Okay, so you're saying that you have one sister that's normal, one sister that's broken. So why would that make it G2?
It happens in G2.
Yes, it happens in G2 phase. Okay. Let's see. Mansi, what do you?
So it can't be G1 because if it was already broken and then it replicates, then that means this is broken already, it replicates, then this is also broken. So both of them will be broken because it replicates itself.
Okay.
So only one is broken. So, and obviously there is a sister chromatid, that means the S phase already happened, and one is broken, so that's what we need to do.
All right. Very good. So, you know what? Okay, I'll just do this. So,
very good G2 or very good S? Explanation.
so. I am gonna create a chromosome. All right. Here's one part of my chromosome. Here's the centromere to my chromosome. And then here's the other part of my chromosome. All right. There's my chromosome. Okay. This is what I have during G1.
Sir, do we have sister chromatids during G1? No.
No. So do you see a sister chromatid?
But you just said G1, the two of them.
This is a chromosome.
It's a chromosome with two.
What
with
is
the
a sister
two
chromatid?
strands. So this is a chromosome with two strands.
No. Your chromosome always has one portion, centromere, second portion. Right? If you look back over here, your chromosome always, right, has one portion, centromere, second portion. One portion, second centromere, second
So
portion.
even if the sister chromatids are not there, the centromere is there, so I didn't know that. Chromosomes do have a centromere only when the sister chromatids show up. So.
Just roll with it for now, Sheena.
Sorry.
Okay, this is just for demonstration. Let's go with it for now.
Sorry.
So, let's say, all right, let's just pretend that there is no chromosomal damage at all. So, G1, this is my chromosome. During S phase, what happens? It duplicates, right? So it's literally copy and paste, right? I have one, and then I create a second one, right? And then they're all stuck together with this centromere. And then, this is exactly what I have carrying into G2, correct? So that's what normally happens. Now let's add some damage in. If we have damage, so let's say that I just chop off a piece of this chromosome. All right. And then I take the rest of it and I just shove it in there. All right. Here, actually, you know what, let's just use a different color so it's obvious. Okay. Here. I have damage to my chromosome right here. There's my damage. Okay. This damaged chromosome goes into S phase. Right? So I'm going to take this damaged chromosome and we're now in S phase. What happens? Duplicates. So I take this chromosome and I duplicate it. Okay. Centromere. And so when I am in G2, where do I see damage to these chromatids? Or sorry, do I see damage to both chromatids or just a single one?
No.
I see it to both, right? So if the damage happened during G1, both chromatids would show that damage during G2. Okay, so that's kind of what Mansi said, right? If you have damage during G1, it's going to be duplicated during S, and you see it on both chromatids in G2. On the other hand, let's say that I've got a regular chromosome, it goes to S phase normally, but then after it exits S phase, X-rays hit this. And so after this exits S phase, X-rays hit one of these sister chromatids. And now we have damage. How many chromatids are affected? Just one. Right? So, if you see only one chromatid affected, that happened during G2. If you see both affected in the same way, that happened during G1. Okay, so because G1 will copy your damage. G2, the damage will be individual.